So we have been talking about dynamic programming so far. In particular, we wanted to talk about approximate dynamic programming today. And one of the major chunk of approximate dynamic programming, especially in today's world, is the case where we are doing cost function approximation, model approximation, value function approximation, and then the policy approximation. And if you think about it, so cost function approximation is basically approximation CT, model approximation is approximating f tilde t, value function approximation is to get an approximation of v tilde t, and policy approximation is getting an approximate pi tilde t. Okay, so these are the four functions that we are generally thinking about. We also have GT less than equal to 0, which is our constraint on the state action pairs, but we don't really tend to approximate those because those constraints are already very simple, like the distance to the vehicle in front has to be greater than something, or the temperature of the room has to be within this band. So a lot of those constraints are very simple and straightforward, so we don't have to worry about those kind of approximation, the approximation of the constraint. But these are the major approximations that we have to do in approximate dynamic programming. And if you think about it, each of these functions are of this form. I'm going to use f as a generic function, but so each of these functions is of the form Rn to Rm. Of course, these spaces could be complex. So if you are doing inventory control or if you are doing airline scheduling problem, then you generally don't have real numbers, you have like natural numbers there. You have like how many packets of chips should we restock, how many ball bearings we should be manufacturing. So many cases these are not real numbers, these are natural numbers, but we'll just assume real numbers for this particular class. And I might be teaching reinforcement learning class next academic year, so 25-26 year. So then we'll go into more complex spaces in that class. That's a 7,000 level class, so I can choose to be more complex in that class. So this class was not complex, just FYI. Okay, so most of the functions are of this type. And what are we given? So if you recall from our early discussion on dynamic programming, what we generally do is we evaluate what the value function is going to be at discrete set of points, and we figure out what the policy is going to be at discrete set of states. So we were trying to solve this problem, minimize over ut ct of xt ut plus vt plus 1 ft xt ut such that gt xt ut is less than equal to 0, and the argmin is pi t star xt, and the min, just the min, is vt of xt. So what we have said is at every time step t, I'm going to pick a point xt1 and I'm going to find out what pi t of xt1 is going to be, and then I'm going to pick another point xt2 and I'm going to find out what pi t star of xt2 is, and of course I'm also going to do vt of xt1, vt of xt2, and so on and so forth, right? This is what we had discussed, and we can store it in a tabular format, and then we can use that table as the ground truth for executing the policy. So this is known as discretization. So what we are doing is discretizing the state space, and whenever we need to evaluate this Vt plus 1 at a specific point, we can do some sort of linear interpolation or some complex interpolation method in order to figure out what the value functions in between these 2 points is going to be. Typically linear interpolation is used, but people tend to use spline interpolation and other forms of interpolation as well between different values of value functions. Okay, so that was our starting point. That's where we started this discussion. Now the problem is as follows. So Elon Musk gave you the job, like we need to go to Mars and come back. That's the job that needs to be done. And you immediately realize that it's a dynamic programming problem. We need to get to the Mars. There is a dynamics involved for the rocket engine. And then we need to go to the Mars, and then there is another kind of dynamics involved coming from Mars back to Earth. So that's the job that needs to be done. And very soon you realize that as much as we would like to use this particular method, it seems to be fairly infeasible. It's infeasible because the state space is huge. This Rn is very, very large for that particular problem. And there is a whole bunch of approximations that are needed to get to Mars and come back. So what are you going to do? What is step 1 of this particular? Yeah.
Can you reduce the dimension of Rn?
Can you reduce the dimension of Rn? Typically you cannot, because remember, the state space of an aircraft is kind of sort of fixed. It has to go in 3-dimension space, and it has to have 3-dimensional velocity, Vx, Vy, and Vz. Okay. So by the way, step 1 is to ask Elon Musk to hire me as a consultant to SpaceX. Okay. What is step 2? So the step 2 is going to be that we need to do all these approximations, and we also need to do look-ahead approximation. So we talked about look-ahead approximation in the previous class. So we'll do look-ahead approximation. So we'll divide the problem as follows. I want to go from Earth to upper atmosphere, and then from there, some physicist had told me that this is the path I need to take. So this is I'll just do a tracking controller along that path. But from here to that particular point in the space, I'm just going to apply dynamic programming. So that's like a look-ahead optimization. So from here to upper atmosphere, I'm going to do optimization. After that, I'm just going to track some specific trajectory as dictated by a physicist or an astronomer who tells me, okay, this is how to get to the Mars. So that's what I'll do. That's look-ahead approximation. And then once I reach the upper atmosphere, I'll do another look-ahead approximation. And what I'll do is I'll try to get from upper atmosphere to the moon as soon as possible using this dynamic programming method. But moon onwards, I'll do whatever the astronomer's policy is. And then once I reach the moon, I say, okay, from moon to Venus, I'm going to do the optimization. After that, I'll just follow whatever the astronomer says. So this is like a look-ahead approximation. That at every point of time, you're looking 10 steps ahead. And then after that, you just use somebody else's policy, whatever that policy may be. And that's the rollout algorithm we talked about in the previous class, or we talked about the tracking algorithm, the MPC. So you can apply any of these 2 methods in order to solve that particular problem. So we did look-ahead approximation. Then the cost function is very complicated. There is some fuel burn happening. There is some tracking thing that needs to be done. There is some orientation of the entire structure that needs to be kept in a specific orientation. So there is a complicated cost function. There is a complicated dynamics. And of course, this value function and the policy is going to also look fairly complicated. So what we will do is we'll do like a function approximation for all of these things. Okay, we'll try to approximate the cost function, we'll try to approximate the model, we'll try to approximate the value function, and we'll try to approximate the policy. So in some cases, the approximation would be easy. So we'll just use linear model as a model approximation. So original model is nonlinear. I remove all the nonlinearity around the equilibrium point, and I use a linear model for the model approximation. The cost function is very complicated, but I'm going to simplify the cost function, take a polynomial cost function, and use that polynomial cost function as my cost function approximation. But then the value function and policy still needs to be approximated in a somewhat non-trivial fashion, and this tabular method is not going to scale for that rocket problem. Okay? A similar problem would appear if Walmart comes to you and says, we need to figure out how to stock for Thanksgiving or how to stock for Christmas. Even before Walmart, the turkey farm and the chicken farm will think about, okay, how many chickens should I start raising in April so that I can meet the Thanksgiving demand, Thanksgiving dinner demand in November. And so there is a lot of complicated dynamic optimization that happens, especially around festivals, around weather events. So if there is a hurricane that's going to come, then we need to figure out how many water bottles needs to be manufactured today so that by the time hurricane comes and devastates an entire area, how many water bottles needs to be delivered to those areas, those affected areas. So a lot of those dynamic optimization needs to be done. And so we need to do this approximation. So what I have done here is I have tried to solve this problem at time capital T, and now I have this discretized values of the state space and the values that needs to be stored. So what I have is a data set which is a tuple xt, I'll use k, I, j, k, I think k is fine, and then ytk, k goes from 1 to capital K, and this is the data set in Rn cross Rm. So this ytk is in Rm and xtk is in Rn, right? So that's what we are trying to approximate. That's the function we are trying to approximate. So this is the data set that I have created. So at every point of time t, I'm going to create this data set. I can create one data set for value function approximation and one data set for policy approximation. And now I need to pick a function class. And today's lecture and Friday's lecture is going to be all about function class. So I'm going to define a function class f theta or just a function class f. And then I want to solve minimum over theta of summation the data set x, y in dt. Let me call this data set dt of f theta x minus y square. Again, I'm using square, but you can pick any loss function. So theta is called the parameter. Typically, theta lies in Rd, and d could be a million dimensional, billion dimensional, trillion dimensional, whatever. It's some dimensional object. And this brings us to machine learning, because this is exactly the problem that machine learning tries to solve, or statistical learning theory. This is the problem that statistical learning theory tries to solve. You have a data set, you pick a function class, and now you need to fit a function in order to get an approximation to Vt or pi t. In our case, we are interested in pi t and Vt. In some cases, I may also be interested in Ct and Ft. So that's what reinforcement learning tries to do. So reinforcement learning it just has the data set about the cost and about the model, and then based on the data set about the cost and model, it needs to it needs to run the dynamic programming. So it needs to figure out a cost function, a cost function, and a model. And then based on that, and based on the dynamic programming recursion, it needs to find a policy and the value function. So this is the subject of reinforcement learning, which we might be teaching next year. If you are around, then you can come to that class. Okay, so but right now we are only focusing on value function approximation and policy approximation, but you can do other approximations as well. Okay, this problem is clear to everyone. This is the problem that we need to solve at every point of time. So at every time t, I do the discretization, I figure out, I solve this problem, and wherever I see vt plus 1, I'm going to replace it with v tilde t plus 1, which is an approximation coming out of solving this optimization problem. So I'll do this v tilde, and then I'll get these discretized values, and then I'm going to fit another function like this. I can solve another problem like this and get v tilde of t, and this would yield pi tilde of t and v tilde of t. And this pi tilde of t will tell you how to send the rocket to Mars. It will tell you how to stock Walmart shelves. It will tell the chicken farmer how many chickens to raise in April for Thanksgiving lunch or Thanksgiving dinner or whatever. And then it will tell you how many bottles to manufacture in order to meet a requirement during a hurricane season. Okay. So what I'm going to do today and on Friday's class is to talk about different function classes f of theta. That's what our goal is to be. Because solving this problem, you know how to solve it using the unconstrained optimization problem. It could be a least square optimization problem, or it could be some other optimization problem, but that's something we've already studied how to solve this problem. So now we are looking at what are the different f thetas that we need to keep in mind. Any questions so far? Okay. Let me erase most of the stuff from the board. Okay. So when we talk about this function approximating class f theta, I want to differentiate between the following different classes. You can have parametric versus non-parametric. You can have random versus deterministic. And then you can have continuous versus discontinuous. Okay, so in the parametric class we have theta that we need to optimize. In the non-parametric class there is no theta. We just can figure out the function approximator without appealing to any parameters. However, non-parametric function approximators are very complex, as a result of which people don't tend to use non-parametric function approximators. Then we have randomized versus deterministic. So I can create this f theta in a completely random fashion, or I can come up with a very specific classes of f theta and then solve this problem in order to get a function approximator. Or alternatively, you could have continuous and discontinuous. So this f theta can have continuous functions within the class, or it could have discontinuous functions within the class. So if you're doing inventory optimization, if you are in the business of selling t-shirts, generally you look at the inventory and you say, okay, I have low, medium or high inventory level. So you don't actually count, okay, how many t-shirts you have. You're like, okay, I see that there are probably 10 or 15 t-shirts, so the level is low, so I'm going to order more t-shirts. On the other hand, if you have like 5 cartons of t-shirt, then you are like, okay, I have a lot of t-shirts, I don't need to order right now. So in those cases, what you have is a discontinuous policy. So you have like a some inventory level above which you want to place the order, but below which you don't want to place the order. So that's a discontinuous function approximator. And so in those cases, you don't want to use a continuous function approximating class, because typically what happens when you are placing these orders, a manufacturer will not send you only 5 t-shirts, like, because that's what your shortfall is. It'll sell you only 100. Like, you can get 100 t-shirts or 200 t-shirts or 300 t-shirts, but you can't get like just 5 t-shirts from a manufacturer. In fact, some manufacturers, they make in millions of t-shirts. So like they'll be like, we can only take orders of 1 million t-shirt. We can't take order of less than 1 million t-shirt, because that's how they have optimized their entire factory, their entire inventory management system, and so on. Okay. So that's in those cases, whenever you have this kind of situation, you need to use discontinuous function approximators, because the continuous function approximators will not make sense for those problems. But if you're sending a rocket to space, everything seems continuous. So in those cases, you want to use continuous function approximating classes. Okay. So let's get into parametric function approximators. So here is how I'm going to construct f of theta. Maybe I'll use f of theta itself. F of theta x equals to summation theta I phi x. I equals 1 to, no, this n is already used. M is also used, M, N, O, P. P is not used, so I'm going to use P. So this is known as a basis function. In your undergraduate class, you might have heard about Legendre polynomial, Bessel function. So those are all basis functions. You can come up with more complicated basis functions like logarithmic basis functions, or you can pick exponential or sigmoid, and those are all very valid basis functions to pick in order to come up with this function approximating class. You can also do basis expansion by adding more phi of x. So let's say your phi of x is x1, x2, x3. Then you can put x1, x2, x2, x3, x1, x3, and then you can put log of x1, log of x2, log of x3, and so on and so forth. So all of this is a way to keep constructing basis functions that you think would improve the approximation error, which is the error here. So whatever reduces the approximation error is a good set of basis functions to pick. This is W3 sigma W2 sigma W1x. This is your neural network. Where theta is actually W1, W2, and W3, and sigma is the sigmoid function. Sigmoid, ReLU, tan h, etc. So any non-polynomial function, this has to be non-polynomial. Okay, so any non-polynomial function will work. So sigmoid, ReLU, tan h, these are the typical non-polynomial functions you pick.
Why non-polynomial?
I'll get to it in a bit. When I talk about universal function approximating theorem, then I'll tell you why non-polynomial is important. So the thing is, if these are all polynomial functions, then in that case, the overall function is actually a polynomial function, because this is just some weights polynomial of weighted average of x, so which is a polynomial, and then this is a polynomial, and then this is a polynomial. So what you have is a polynomial, which basically falls within this class. Any other question? Third is reproducing kernel Hilbert space. And you know, kernel is used quite a lot in a large number of different fields. So don't get confused between different notions of kernel. So this is a specific kernel that we'll be talking about today. But if you look at probability theory, then there is a kernel in probability theory. And if you look at functional analysis, there is a kernel in functional analysis. And then when we talk about non-parametric function approximator, we'll talk about a different kernel in that particular topic. So here f theta is basically function f theta of x, which is summation theta I k of x xi. I goes from 1 to p. But this kernel k, the kernel function capital K, has some specific properties that I'll talk about. So it looks very similar to the basis function approach, except that the basis function actually comes from a kernel. And in the kernel function, K is a kernel function. K maps Rn cross Rn to R, called a kernel function. And it satisfies that any matrix A Yes.
In the second case, is theta supposed to represent like a layer in that specific case?
It's the weights of all the layers.
Of all the layers?
All the layers. Yes.
So in the machine learning class that's taught 5,000 something, we talk about the kernel with respect to the basis function as being like the inner product of the basis function with itself.
That's another notion of kernel. It's not the same. Yeah, it's not the same as this one. That's why I said people use kernel in very different contexts. So every context has its own nuances of kernel. So this is for reproducing kernel Hilbert space. So K is known as the kernel function, and you pick a set of points in the space, right? And you construct this matrix A of K xi xj, right? And this is an S cross S matrix, like it's a square matrix. And it turns out that it should be positive definite. So it should be symmetric and all eigenvalues should be greater than 0. Then it's a kernel, then it's a valid kernel function. There are some examples of the kernel functions which I'll write here. Is this part visible to everyone? It's visible to you, right?
Why is it positive definite?
Why is it? That's the requirement on the kernel. It's not a valid reproducing kernel if this matrix is not a positive definite matrix.
Okay, it's just okay.
That's just a requirement on the kernel. Otherwise, it's not kernel. Okay. So K of x comma y is exponential minus norm of x minus y square over 2 sigma square exponential minus x minus y over sigma x transpose y plus 1 raised to 2n plus 1 or 2n plus 1 tan h x transpose y minus alpha So these are all like, there are multiple such kernels. You can look up the theory on reproducing kernel Hilbert space and you will find, or you find a paper on it, there will be like 15, 20 different types of kernels written there. Okay, so these are just examples of some kernels. So this is a Gaussian kernel, this is a Laplacian kernel, this is a polynomial kernel, this is a, I don't recall what it's called, but anyway, it's also a valid kernel.
What makes it a reproducing kernel?
That's a big can of worms. So if you go back to my, I can send you the video to the video lecture to my class on reinforcement learning back from 2020. So I go into the mechanics of what reproducing kernel Hilbert space does, and you can see why it's called a reproducing kernel. But basically, it requires you to know what a Hilbert space is. Only then you can understand what a reproducing kernel in that Hilbert space means. And
is there a really good Wikipedia article you recommend? Or
Wikipedia will definitely give you a good idea.
Okay.
But it implicitly assumes that you know what Hilbert space is. Then the fourth kind of function approximating class is decision tree. This is basically f theta of x is so this is indicator function. This is 1 if this condition is satisfied, and it is 0 if this condition is not satisfied.
same basis function?
You can pick whatever basis function you want.
Okay.
Yeah, you can come up with complicated basis functions as well. And you can also pick this threshold. So theta here is both theta I and alpha I. Both of those are parameters to be picked.
Theta is theta I, phi I, and alpha I? Or
Yeah, kind of. Yeah, there's a whole bunch of weights. Maybe I can write it as wi. And then theta would be w, alpha, and then phi. All these three things together. Yeah, we have not used w, so I think it's fine. We can use w as. Okay, so decision. So I've written a simpler form of decision tree, but typically you can make complex decision trees as well. So this decision tree is basically saying I have phi1 of x, and is it greater than alpha I, less than equal to alpha I? If it is greater than alpha I have 0, and then I have 1, and then I have phi2 of x, and this is greater than phi1, so this should be alpha 1, alpha 2 less than equal to alpha 2, and this is 0 and this is 1. And then I will have the weights here as w1 and then w2, and then I will add it up and give the output f theta of x. So that's one way to think about decision tree, but this is a shallow tree. It's a shallow tree because there is only one node here, and then you get the final leaf node. But you can make complex decision tree. So I'll give you an example of a complex decision tree once you note this particular part down.
Because it's like in machine learning, we call small decision trees like this a stump.
Yeah.
Is that the same?
Yeah, it's the same thing. So you can create complex decision tree by saying that if my x1 greater than 5 less than equal to 5, then I'm looking at x2 here and I'm looking at x3 here, greater than 3 less than equal to 3, greater than 6 less than equal to 6. And then you can assign it some value like 3, 4, 5, 6. So that's a decision tree with two depth 2, because now you have two sets of nodes where you are doing this, making this decision. And then you can create many such decision trees, and then you can add W1, W2, add them up, and you get f of theta. But writing this kind of decision tree here is going to take a little bit of effort, so I'm just showing it to you in a graphical fashion.
So the more branches you have, the more weights you're saying? Because you use
No, the weights is the number of trees you have. So those are the number of weights you need to pick. But each tree will have some value at the end of the node. So this is Wi, and this is, so here my phi1 of x is x1, and then here I have picked another phi2 of x, which is x2, and here I have taken phi3 of x, which is x3, and so on and so forth.
So f of theta, capital F of theta is then like
It's a repeated application of exactly this kind of sequence. Okay, so this is one tree, this is second tree, and then you are taking a weighted combination of the trees in order to get your f theta of x. That's a decision tree. You can call it, some people call it regression tree, some people call it decision tree because of some nomenclature, historical nomenclature. But these are all basically trying to do the same thing, which is look at the values of x, figure out whether it's high or low, and based on that come up with some numbers and then add those numbers up in order to approximate a function. Now one thing you will notice is you can have a basis function that is that is continuous, in which case this f theta will be continuous. If this is discontinuous, f theta will be discontinuous. This will always be continuous because sigma is a continuous function, and this is what is that called? Composition of continuous function. So therefore this is a continuous function. Reproducing kernel Hilbert space, as you can see, these are all continuous kernels. So reproducing kernel Hilbert space is also going to produce a continuous function. And decision tree, as you can see, it's a discontinuous function. So it will produce only discontinuous function. It will never produce continuous functions. So how do you know which function approximating class is a good class versus a bad class? Okay, so that's a question that one should ask. Is this a good class of function? Is this a good class of function? Is this a good class of function? And so on. So that is studied under the umbrella of universal function approximation theorem. And many trees have been cut, many books have been written, many papers have been written on universal function approximation theorems. So lots of universal function approximation theorems exist in the literature. So the ingredients here are as follows. You define your function class f and the norm on the function class f, and then you define f theta. And then the results are of this type. For every epsilon greater than 0, there exists a function f theta in f theta. And for every epsilon greater than 0, for every function f in capital F, there exists an f theta in f theta such that f theta minus f is less than epsilon. Yes.
Is that basically saying like approximate any function?
Correct. You can approximate any function in this function class by a function in this class under that particular norm, the norm on this function space. Okay?
Any norm?
Not any norm. Typically, the approximation theorems are under a certain norm. So you pick continuous and bounded functions over a set. This would be the infinity norm, and this would be the neural networks. And then you have a universal function approximation theorem. And this could be convex increasing function. This could be infinity norm. And this is the set of neural networks with convex increasing sigma, like sigmoid, for instance.
How are you choosing infinity norm? Like, what's the intuition behind that?
So basically, the infinity norm f minus g infinity is given by sup of x fx minus gx.
Why is that the logical choice, though? You're like
Why is it logical? So basically, just like you measure the distance between 2 points using L1, L2, L infinity norm, like there are all these norms that we have discussed. When you have two functions, you can also use L1, L2, L infinity norms. So this is just one of the norms. You can also pick L1 norm, but then this universal function approximation theorem will generally not hold.
I guess I'm not seeing why that's true. Like,
I mean, so just like you pick some norm in order to measure the distance between 2 points, in order to prove universal function approximation theorem, you have to pick some norm. So infinity norm is the one for which most of the results have been proven. It's easier to prove results in infinity norm.
okay.
Okay. So if you look at continuous and bounded function, so if you look at, let's say you are sending a rocket into the space and you expect the value functions to be continuous and bounded, which is going to be the case. If it is continuous and bounded, then you want to use neural network or a reproducing kernel Hilbert space, because you know that for every value function that exists in the world and for every epsilon greater than 0, you can always find a neural network so that the distance between the neural network and the actual value function will be less than epsilon, which is a desirable thing to have, because you can make sure that your epsilon is very small, so that you are getting a very good approximation of the true value function by going through this training process. Okay. So what do we know about some of these things? So basis function, it's not a universal function approximator, because you can think of basis function as a line in the function space. So you're just projecting a function onto the line, and therefore it's not a good approximation of the true function. But it kind of works very well if you, so for instance, in the case of linear quadratic problem, we knew that the basis function is going to be just a quadratic function, right? And we just want to optimize the quadratic function. So theta would be just the matrix, Q matrix or K matrix that you have already done in your assignment. So in some cases, it kind of sort of works. In most cases, like if you want to send the rocket to space, or if you want to optimize Walmart's inventory management, that basis function will not really work very well. Neural networks and reproducing kernel Hilbert spaces, these are universal function approximators for continuous and bounded function under infinity norm, which means you get a very good approximation of the true function if you use one of these two methods. Decision tree, on the other hand, it's I haven't seen any results on the universal function approximation property for decision tree, But typically, it works very well for discontinuous problems. So inventory management kind of problem where you can either pick 0 or you can pick 1,000,000, but you can't pick anything in between. So then decision tree works out very well in those cases. So yeah.
I was just going to say, so it might work for your problem, but it may not have like a guaranteed approximation.
That's right. It will not have guaranteed approximation. So that's the problem.
Okay.
So one thing that you would see a lot of people do is pick a problem, pick a function approximating class, and then write a paper about it without really looking into the guarantees. But if you are interested in getting the guarantees, you have to look at this particular theorem and then use that for guarantees. Okay. Most of the time, if you're working in industry, you don't really look for theoretical guarantees. All you're looking for is, does this work or it doesn't work? In which case, you can pick whatever function approximating class works well. So if you're doing airline scheduling and you need to do the airline scheduling on a daily basis over the next 1 month horizon, and the neural network takes 5 days to complete the scheduling, then that becomes a problem. If reproducing kernel takes 10 days, then it becomes a problem. But maybe the basis function does it in 5 minutes, and then you probably want to use the basis function method rather than doing something more complicated. So computational bottleneck, memory, all of these are important criteria to decide which function approximating class you want to pick. There is a very nice training algorithm for decision tree called XGBoost. It's very, very fast. So some people have started using, so instead of training neural network, which requires a huge computational power, you can use decision tree because it requires very little computational power and very little memory. So even on my laptop, on my regular laptop, I can train a very complicated decision tree, but I can't really train a complicated neural network. So I get the proof of concept very quickly if I'm using decision tree. And then if I want to do a full-blown implementation in an industrial setting, then I'll probably use neural network or something. Okay, just something to keep in mind. Yeah.
When you were writing the function f, you said that the approximated linear version of it is around the equilibrium.
Right.
What is equilibrium?
Okay. I can talk about that. That is separate from the topic that we are discussing, but I don't know. Maybe I'll take the questions on this part first, and then I'll talk about what that equilibrium means. Any other question on this part? Okay. So those were all the parametric function approximators. So as you can see, all of these required parameters. So there is parameter here, there is parameter here, parameters here. So these xi's are also parameters, by the way, because you can pick whatever xi you want for RKHS. And then you have parameters here. So these are all parametric function approximators. There is no randomization. But how can you make a random function approximator? You can pick each of these W to be random. So you can pick W2 and W1 to be random, but W3 is what you are going to train. Then it becomes a random function approximator. You can pick these xi's randomly in the space. Okay, then it's a random function approximator. All you are doing is optimizing theta I. You're no longer optimizing xi. Here you are optimizing W3, but you're not optimizing W1 and W2. You pick the Gaussian matrix as W1 and W2. This basis function can also be picked in a completely randomized fashion. So you can create all these thresholds, alpha I, these less than 5, greater than 5, 3, all of this can be done in a completely randomized way. And that gives you a random function approximator. So XGBoost, if I remember correctly, does random function approximator. And that's why every time you run XGBoost, you get a completely different tree because it's all random, but it still gives you very good approximation. And because it's randomized approximator, it actually executes very fast because there's a whole bunch of optimization it doesn't need to do. It just picks a random number. And ultimately, if you have a very bad function, the W1 will become 0. So W1 is all it optimizes. Everything else is not optimized. So what XGBoost does is it optimizes what value to pick here. So x1, x2, x3, which one will go here, which one will go here. So that's the only decision it makes. And then it makes the decision on W1 and W2. But whether it's greater than 3 or less than 3, greater than 5 or less than 5, all of that is completely random. Okay. So that completes the discussion on the parametric function approximator. So I'll talk about non-parametric function approximator, and then I'll talk a little bit about random function approximator in the next class. Now, one of the questions that emerged is, how do you do linearization of the model around the equilibrium? So let me give you that information. So this is my rocket, and this is my space, and this is Earth, and this is the trajectory of the rocket. And so here I will be at xt. No, I want to give it some other name. Let me call this yt. This is the true state of the rocket, zt, and then I'm going to call this distance as xt. Okay. So what do I have? I have like yt plus 1 or zt plus 1, ft, zt, ut, right? I'm going to replace zt plus 1 as xt plus 1 plus yt plus 1, ft, xt plus yt, ut, right? Now, yt is a large number, xt is a small perturbation, right? So I can do this linearization around xt. I can take the first order Taylor series approximation, and so I get ft yt ut plus gradient of x ft yt ut times xt, right? And this is Rn cross n matrix, because remember ft has n components, and this is gradient with respect to x, so I have Rn cross n. So it's a square matrix that gets multiplied by xt. But that only works if you know that xt is going to be a small perturbation to the trajectory. So if there is small crosswind and all that. But if you are sending this in a hurricane or something, if you're flying a rocket in a hurricane, then this approximation may not work, because you can be way off. Okay. So this is how you get the linear approximation. So I did a linear approximation around the state. I can also do it around the action, and then I get like a good linear system for sending the rocket to space, which works under normal circumstances but may not work under extreme circumstances. Just something to keep in mind. So if you are sending something to Jupiter, Jupiter has like 175 miles per hour wind at every point of time. So whatever linearization you will do will not work on Jupiter, but it will work on Earth, it will work on Venus, it will work on Moon. Moon doesn't have an atmosphere, so everything works out well. Venus doesn't have as much wind. Mars doesn't have as much air, so it also doesn't have as much wind. So, you have to, that's roughly the way you should decide what function approximator to use, what technology to use, should I linearize, should I not linearize, so all of that thing goes into the decision-making process. The inventory problem that you solved in your optimization homework, assignment 6, the state space is always, the state transition function is automatically linear by virtue of how you are producing and how you are consuming your item. So you don't really have to do any linearization there. The model automatically is very simple and straightforward. So that's all I have for today. We'll meet again on Friday, and we'll go into more function approximating classes on Friday. Thank you.